Alright, what's going on? This video we're going to look at linear approximation and differentials. And you know, this is pretty easy. It's not bad at all. So let's look at it. We've got linear approximation or tangent line approximation of f at a, okay, when x is some number a. So that's L of x is equal to f of a plus f prime of a times x minus a is called a linearization of f at a. So you can see here we've got our point here, a f of a. We've got our curve, fy equals f of x, and here's the line L of x, or your tangent line. Look, all this is an equation of a line. You did this in algebra. All right, so look, remember if you have a slope m and you have a point x1, y1, all right, or something like that, then what? You got y minus y1 equals m times x minus x1. Look at that. See that? It's just the y1. See, y is equal to y1 plus m times x minus x1. See, it's a slope at the, and here's your point x1, y1. Well, look, isn't that the slope? The derivative evaluated at that point at a, that's the slope of the tangent line. And then what's your point? Your point, the x value's a. Well, what's your y value? Well, if it's f of x, then you plug a in for x, and there's your f of a. So there's your point. See? So your y coordinate here, y coordinate here. So your y coordinate f of a, there's f of a. There's m, your slope, right here. See that m? There's your slope, f prime of a, x minus the x1. Or in this case, x minus a. It's the same thing. All right? That's all you're doing. So don't make this more complicated than what it is. Well, I mean, it's really not complicated at all, but hopefully that, you know, it gives you an idea of what you're doing. So let's see, they want us to find the linearization of the function f of x is equal to the square root of x plus 3 at x equal 1. At, well, x at a equals 1, and use it to approximate 3.98, the square root of 3.98, and the square root of 4.05. All right, so what do we need here? Well, we've got L of x is equal to f of a plus f prime of a times x minus a. All I did, I just wrote this down again so we'd have it down here so we can see it. All right, so we've got f of x is equal to the square root of x plus 3. All right, now let's just see what all we need. All right, we need a. Okay, so they give us that. They tell us that. Let's just write everything down here. A is equal to 1. Okay, we need f of a. Well, let's see, f of 1, okay, because a is 1, is equal to the square root of 1 plus 3, which that's 2, okay, and then we need the derivative evaluated at 1. So let's take the derivative of this thing. So I've got f prime of x is equal to, now if you watch my videos, then I have a shortcut for finding the derivative of a square root. And I'm going to write it down, the derivative of this. And if you want to watch the video on where I go over it in more detail, just search my channel for finding a shortcut for finding the derivative of a square root. So the shortcut is we're taking the derivative of this, so 2 times whatever the square root is, that goes in the denominator, and then the derivative of what's underneath the square root goes in the numerator, so the derivative of x plus 3 is 1. And so there's your derivative. All right, and yes, if you didn't catch how to do that, then you can rewrite f of x as x plus 3 to the 1/2 and use the chain rule. All right, you can do that. But that shortcut is it's a lot easier. So just remember, the square root, that goes in the denominator times 2 always. And then whatever's underneath the square root, the derivative of that goes in the numerator. All right, so we need this evaluated at 1. So I've got f prime of 1 is equal to 1 over 2 times the square root of 1 plus 3, which that is 1/4. So I've got everything. All right. Now, let's plug everything in. So I get L of x is equal to f of a, so f of 1 is 2, plus f prime of a, which is 1/4, times x minus a, and a is 1. And so I get L of x is equal to 2 plus 1/4 x minus 1/4. And so I get L of x is equal to 1/4 x plus, and that's 2, so that's going to be 8 over 4, so that's 7 over 4. All right. So that's the answer to find the linearization of the function f of x equals the square root of x plus 3 at a equals 1. That's the answer to that. That's the linearization of the function. Now they want us to use it to approximate. All right, so basically what we've got is our linear approximation is the square root of x plus 3 is approximately 1/4 x plus 7/4. So we can use this to approximate the square root of 3.98 and the square root of 4.05. So let's look at the square root of 3.98. So that is approximately, that's going to be what? 1/4 times 0.98 plus 7/4. All right, so you might be wondering, well, why 0.98? Because they wanted us to find 3.98. Well, remember, we have the square root of x plus 3, and so that's going to be the square root of 0.98 plus 3 is equal to the square root of 3.98. So in this case, x is 0.98. See, that's your x. 0.98 plus 3 gives us the 3.98. And then I'll just go ahead and tell you. So for 4.05, what would x be? 1.05 plus 3 is 4.05. Okay? All right, so when we plug all of this into our calculator, we're going to get 1.995. And there's your approximation. And then we want to do the square root of 4.05. Well, the approximation there, that's going to be 1/4 times 1.05 plus 7/4. And you punch that into your calculator, you get 2.0125. And there's your approximation using a linear function. Now, let's grab the calculator and put in square root 3.98. Punch that into the calculator and let's see what it gives us. The calculator answer is 1.994993734. So you can see it's pretty accurate there. And then we've got the square root of 4.05 in the calculator. That's 2.0124618. This answer and this answer, that's what the calculator gives us. All right, so it's a pretty good approximation, isn't it? All right, so let's look at the next example. All right, so for what values of x is the linear approximation, this, which we just found, accurate to within 0.5 And then what about accuracy to within 0.1? All right, so basically what I want to know is how far out can I go? See, here we went out, let's see, we went out, see here x was 0.98 and x was 1.05, but how far out can I go to where my accuracy will be within 0.5? Okay, you can see the accuracy here is pretty good. These numbers aren't off by much. Okay, so that has a good accuracy, and and I mean x is not far away at all. Okay, but let's see what we can do, and it'll make more sense when we look at a picture. I'll pull a picture up in a minute, and you'll see what I'm talking about. All right, but basically what we want to know is I want the difference in this calculation and this calculation. So if I take this calculation minus this calculation, I want that difference to be less than 0.5. Okay, so if I take the square root of x plus 3 minus 7/4 plus x over 4, and look what they did. You see how they wrote theirs? I just wrote mine. I wrote mine in the mx plus b form. It doesn't matter. They just put the x up here and put this term at the end. It's the same thing. Okay. All right. So I want this to be less than 0.5. But remember, sometimes when I do this minus this, I may get a positive number. I may get a negative number. Okay, so basically this needs to be within negative 0.5 and 0.5. How would I write that? That would be the absolute value of this, right? Because if I do this minus this and I get 0.1, well, that's within the 0.5. Or if I do this minus this and get negative 0.1, well, and I take the absolute value, that's 0.5 also. All right. So basically it needs to be between negative 0.5 and positive 0.5. And so that's where this absolute value comes in. And then if you remember from college algebra, do you remember when you had the absolute value of x is less than k? You would rewrite that as negative k less than x less than k. Remember when you were doing the absolute value inequalities? Well, that's what we're going to do here. So that's going to be negative 0.5 less than the square root of x plus 3 minus 7/4 plus x over 4 less than positive 0.5. So that's what I need it to be in between. All right. And so what I'm going to do now is I'm going to subtract square root of x plus 3, okay? Because I want my approximation, which is this, to be within the 0.5. Okay? So I'm going to subtract this. I'm going to get this in the middle. I'm solving for 7/4 plus x over 4. And so that's going to give me negative square root x plus 3 minus 0.5 less than negative 7/4 plus x over 4 less than negative square root x plus 3 plus 0.5. And then I've got to multiply through by negative 1 to get rid of that negative. So that's going to be square root x plus 3 plus 0.5. Remember, reverse the inequality symbol. 7/4 plus x over 4 greater than square root x plus 3 minus 0.5. I multiply through by negative 1. Now let's rewrite it with the smaller term first. So that's going to be square root x plus 3 minus 0.5 less than 7/4 plus x over 4 less than, see, I'm keeping this right here, pointed at this, see there, I'm just writing it over here, and that's square root x plus 3 plus 0.5. All right, so, I mean, basically we're solving for x here. We want to get x by itself. But that ain't going to happen there, okay? That's not going to happen, is it? So what do we do? Well, you're going to have to pull out some software or pull out a calculator, okay? If you got one of those big TI calculators, one of those fancy ones that does all the graphs and everything, you can use one of those. But basically what we're going to do is we're going to graph this, this, and this. We're going to graph each one. So let me pull that up. I've already done that. Well, why is it? Oh, I'm sorry. Mashed the wrong one. All right, so here we go. So you can see that the green, let me move this out a little bit. All right, so the green function here, that's this one. Okay, that's the square root of x plus 3 plus 0.5. The red one is the square root of x plus 3 minus 0.5. And then you've got your square root of x plus 3. That's the function right there. And then here's our tangent line. See, this is our approximation, this black line right here. And what we're doing, we want to know when is this tangent line between the red and the green curve. See, between this one and this one. When is it between those? And so you can see here at point A and point B. All right. And so what I did is after I graphed these, you can insert a point into this. By the way, this is called GeoGebra. Best graphing software that's free. It's the best one out there. Download it and install it, or you can use it on the internet. And you can also install the app on your phone. All right, so what I did is I just inserted a point, and I'm not going to go over how to use GeoGebra, but I just clicked on to add the point, and I just clicked near where I thought they would intersect, and it'll snap to that intersection. So I inserted that point, and then I inserted this point here, B, and then you can see point A here. That gives me an x value of negative 2.66. So that x value. And then B has a x value of 8.66. All right. And so the x values where this is within 0.5 would be from negative 2.66 to 8.66, and that is for 0.5 to have an accuracy within 0.5. Now to have an accuracy within 0.1, look, it's the same thing. I'm not going to go through all of this again. See where the 0.5 is? That would just be a 0.1. Okay, work the exact same way. But for the 0.1, it would be, well, I'll tell you what, let's just pull this up, and all we have to do is click in here, and I can modify this. I'm going to change this to 0.1. Did it do it? Let's see. Nope. Let me click in there again. So I'm going to do that. 0.1 and hit enter. And you can see it's already moved, and I'll show you something else that's pretty neat too. And then we'll click here, and we will change this to minus 0.1, hit enter. And so let's kind of increase this a little bit. But what I want to show you that happened, what's neat here, is once you draw that first one and you establish those points, you see how everything moved. See, the 0.1, that's a smaller tolerance there, isn't it? Between negative 0.1 and 0.1, that's a smaller. So you see how the green and the red curves, these two here, how they got closer. And look, since I already put the points on there at the intersection, they automatically move. You see that? And so you can see now our x values here. The x coordinate for A is negative 1.13, and the x coordinate for B is 3.93. All right, and you know, that's what we would expect. We wouldn't expect it to be so wide, because instead of 0.5 accuracy, it's 0.1. That's smaller. So that's going to be, so for the 0.1, that would be negative 1.13 to 3.93, and that would be the accuracy to within 0.1. All right, and that's what they're wanting you to do there, and hopefully by seeing the picture here, that makes it, you know, you can understand more of what we're doing. See, we want the solutions here. We want the solutions to be within the two graphs, the green and the red graph. And you can see once we get past this point, you see how the line gets above the green one, and here the line gets above the green one also. So that's outside of that accuracy of what we want. All right. So there you go. There's that. That's your linear approximation. Okay. It's just this equation of a line is what you're finding. All right. So now differentials. So differentials, we've got dy delta y. So the differentials is the idea behind linear approximations are sometimes formulated in terminology and notation of differentials. So if we have y equals f of x, where f is a differentiable function, then the differential dx is an independent variable. That is, dx can be given the value of any real number. The differential dy is equal to f prime of x times dx. And delta y, that's this right here, that is f of x plus delta x minus f of x. Now, you've got delta x, we've got dx, so dx is equal to delta x. Okay, that's how far we move over this way. And keep in mind, that's going to be a small number. Now, dy and delta y, see, delta y is this. It's from this point, and so if we got a point here, that's going to be that change there in that y value. You see that? From this point to this point, there's your dx or delta x, and there's your delta y. That's the change in your y. And then the dy, that's going to be up to the tangent line here. Okay, that's that difference. But what we're saying is we can get a pretty good approximation with dy. We can approximate delta y with dy. So you can see, look, see, if this point here, see, you've got this point here has an xy coordinate. This has an xy coordinate. All you're doing is subtracting the y coordinates. See, if this is the point x, f of x, you see that? And then this point right here, well, if we go over delta x, that's x plus delta x, you see that? And then what's the y coordinate? F of x plus delta x, right? That would be that y coordinate. And see, all you're doing is you're subtracting the y coordinates. That's all you're doing there. All right. All right, so let's look at this. So it says compare the values of delta y and dy if y is equal to, so we've got y is equal to, now let's write f of x. Y is equal to f of x equals x cubed plus x squared minus 2x plus 1. And I tell you, let's write y. Y equals that. Y equals that function. All right. So for part A, it changes from 2 to 2.05. So let's work on A first. All right. So for part A, all right. So what do we have here? All right. So we've got to have an x, and we've got to have delta x. All right, so we've got x is equal to 2. We're going from 2 to 2.05, so x is 2, and then delta x is equal to 0.05, which, remember, this is the same thing as dx. All right, remember delta x is equal to dx. So, I mean, what do we want to find first? It don't matter. How about we find delta y first? So remember, delta y is equal to f of x plus delta x minus f of x. All right, so let's see what we've got. We've got f of 2 is equal to 2 cubed plus 2 squared minus 2 times 2 plus 1. And that is equal to 9. And then we have f of 2.05. Because remember, x is 2, delta x is 0.05. So 2 plus 2.05 is 2.05. So that's 2.05 cubed plus 2.05 squared minus 2 times 2.05 plus 1. And when we punch that into our calculator, we actually get 9.717717 625. I don't think I didn't run off the screen. All right, so we get delta y, which is f of 2.05 minus f of 2, right? That's what it is. 2 plus 0.05 is 2.05, and then f of 2, and that's going to be 9.717625 minus 9, which is 0.717625. And there's the answer for that. All right, so that's delta y. Now let's find dy. So dy is equal to the derivative of this, which is what? 3x squared plus 2x minus 2 times dx. Remember, see, dy is the derivative of the function times dx. So I took the derivative of f of x and then times dx. And so I get dy is equal to 3 times 2 squared plus 2 times 2 minus 2. And then that's times 0.05. And that, let's see, what does that give us? That gives us 0.7. All right, and there's your answer. So you can see it's not off by much. All right, and keep in mind delta x is 0.05, so you know we're a little bit further away there. All right, so let's do the same thing from 2 to 2.05. Let's see if the accuracy looks a little better on this one. All right, so for part B, I've got x is 2. I've got delta x is 0.01, which remember that's the same thing as dx. Okay, it's the same thing. So let's find delta y first, which is f of x plus delta x minus f of x. And so we've got f of 2 is equal to, let's see, that's going to be 2 cubed plus 2 squared minus 2 times 2 plus 1. And that gives us, let's see, what is it? Oh, well, we've already calculated that. That's 9. Okay. And now I need f of 2.01, which is 2.01 cubed plus 2.01 squared minus 2 times 2.01 plus 1. And that gives us 9.140701. And so I get delta y is equal to f of 2.01, which is the 2 plus 0.01 minus f of 2, which that's going to give me delta y is 9.140701 minus 9, which is 0.140701. And then let's go ahead and find dy. Well, we already took the derivative up here. We're just using this. We're going to use this function again, plug it in. So that's what, 3x squared plus 2x minus 2 times dx. And we're right here at the other problem too, aren't we? So we get dy is equal to 3 times 2 squared plus 2 times 2 minus 2, and then dx in this case is 0.01, and when we punch that into our calculator we actually get 0.14. And so there's dy, there's delta y. So you can see this one right here looks to match this a little better than what we did up here. Okay, so, and which makes sense because dx, or delta x, it's smaller. It's 0.01 versus 0.05. Okay, so you can see, like, see if we have a curve, see like if 0.05's out here, well, here's that gap between them. But if delta x is 0.1, then we would be about right in here, and you can see that gap there is smaller, so the calculations aren't going to be off as much the smaller dx is. All right. All right, so last example here, we've got a word problem. It says the radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere? All right. So first thing we know, what we need is we're talking about volume. Okay. What is the maximum error in using this volume of the radius to compute the volume of the sphere? So the volume of a sphere is what? That's 4/3 pi r cubed. And so basically all we're going to do is we're going to find the differential of this. All right, so I've got, well, and let's keep in mind what r is. R is what? R is 21. Okay, that's what we say, the radius of a sphere, we measured it to be 21. And then our error in measurement is 0.05. All right, and so we've got dr is 0.05. That's our error. And so I've got dv is equal to 4 pi r squared times dr. So when r is 21 and dr is 0.05, I get dV is 4 pi times 21 squared times 0.05, and that is equal to about 277 cubic centimeters. Okay, so that's the maximum error in the calculated volume. Okay, that's what they were asking for, the maximum error in the calculated volume. All right, so now let's look at this. I know I didn't write this down. Okay, so the error seems to be kind of large. All right, so what about relative error? Okay, so let's find the relative. The relative error. All right, so the relative error, that is given by the error in the volume divided by the volume. Okay, delta V over dV, or dV over V, right? That's what we've got. We've got dV over the actual volume. And so dV, that is what? What is that? That is 4 pi r squared times dr, right? That's what we calculated here. And then the volume is what? 4/3 pi r cubed. All right. And so we can see this is going to be, now see, 4 divided by 4/3. So let's just do that real quick. That's going to be what? 4 times the reciprocal of that, 3/4. Those cancel. So we're left with a 3 up here. The pi's cancel out. And then that's going to go out, and I'm left with r down here. So that's dr over r, right? So the relative error in the volume is about 3 times the relative error in the radius. See, here's your relative error in the volume, here's your relative error in the radius, and you can see the relative error in the volume is 3 times your relative error in the radius. So the relative error in the radius, so let's do that. Let's see. The relative error in the radius, all right, so that's going to be that's dr over r, right? Now keep in mind, this right here, that's the relative error in the volume. This dr over r, that's just the relative error in the radius. That is equal to what? Dr, which is 0.05 over 21. Oh, where'd you get that? Where'd you get that? Well, there's dr and there's r. And so we can see that is about 0.0024. That's the relative error in the radius. And then now let's look at the relative error in the volume. Relative error in the volume. Well, that's dV over V, right? So that's going to be what? Well, that's just 3 times this, right? Right? See, we got it right here. See this right here? That's the relative error in the volume. So it's basically 3 times 0.0024. So we've already calculated it here. So that's going to be what? 0.0024 times 3, which is, let's do 0.007. This is your relative error in the volume. There's your relative error in the radius. And then we can also look at it as, that's the relative error, and then you've got percentage errors. We can look at those, and all that is That's just converting these to a percent. That's 0.24%, and this would be 0.7%. All right. Okay, so errors, that's expressed as a percentage error of 0.24% in the radius and 0.7% in the volume. All right. So, I hope this helped. It's really not difficult. It's kind of like a bunch of algebra, especially the linear approximation. I mean, we are taking the derivative to find the slope, but then we're just going back to algebra using that point slope formula. They just solved it different and used different letters. Okay, that's what happened. So hopefully this helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I will see you later.